everyone, Physics in the Flesh is back with more circular motion problems. Ball swung in a vertical circle. A ball at the end of a string is revolved at a uniform rate in a vertical circle of radius 75.0 centimeters, as shown below. If its speed is 3.80 meters per second and its mass is 0.301 kilograms, calculate the tension in the string when the ball is A, at the top of its path, and B, at the bottom of its path. So this problem is really nice. They already gave you the forces drawn in the diagram. This helps a lot. This makes the rest of the problem a lot easier. So you've got this ball, it's going around in a circle, vertical circle, okay, very important. Gravity plays a role in vertical circles, not in the horizontal ones. Okay, so when the ball's at the top, notice that both the weight and tension are going down towards the center of the circle. But when the ball's at the bottom, only gravity is going down, as it should be, but force of tension is going up. Okay, so the force of tension is caused by the string, and the direction is in the direction that the string is at that moment. Okay, so at the top of its path, we have to find the tension, and at the bottom. Okay, so in order to find the force, the first thing I'm thinking at this point is, well, to find the forces, I'm going to need net force. That's Newton's second law. Newton's second law also involves centripetal acceleration. So I'm going to look for that first. AC equals V squared over R. It tells us the speed 3.80 meters per second. Okay, the vertical circle has that radius, so this is a given already. So 3.80 meters per second squared divided by 75. Now that's in centimeters, right? So if you want to put it in meters, put a 0 in the front, 0.750 meters. Done. Okay, calculate that through, you get AC equals 19.25 meters per second squared. Okay, so we're already 1/3 of the way down the problem. Now, we're going to start with what's happening at the top first. Now, because we've got two different situations, I'm going to do two different positive directions. Okay, so when we're at the top, because both forces are going down, I'm going to let down be the positive direction. Although it really doesn't matter, your signs will just be different. Okay, so I'm going to start with my F net equals MA. If you're wondering why I didn't just jump into F centripetal, it's because I want to show you where that comes from. Okay, so previously in the fourth section of videos, we were looking at net force is equal to mass times acceleration, Newton's second law. That's when you're working in a linear fashion. Okay, but when you start going in a circle, you still have a net force acting on you and there's still an acceleration, except in this case, it's not your speed that's changing the acceleration, it's the direction, the other component of velocity. Okay, so the net force when you're moving in a circular direction is called FC or F centripetal, centripetal force. Okay, not to be confused with centrifugal. This is centripetal. Okay, so that's equal to MA centripetal. Okay, so this is still Newton's second law, just for circular motion. Okay, so now, centripetal force, any forces that point towards the center of the circle. Well, check it out. I've got force of gravity going to the center and the tension at the top. I've labeled them different. Now, you might have heard me in the previous video saying if it's the same string, it's the same tension. And while that's true for the ramps, in this question, we know that when the ball's on the top versus the bottom, the tensions cannot be the same, right? Because in one case, the ball's above the string, in the second case, it's below. Okay, so there's a few different things going on there. So at the top, we've got mg going down in our positive direction. We've got ft1 going down in the positive direction, and that's equal to mac. We are looking for the force of tension, so let's put that mg to the right. So ft1 equals mac minus mg. Take a look, we've got mass in both terms, so mac minus g. Now it's simple, plug in the values. Okay, mass is given to us as 0.301 kilograms. A, we just found 19.25 meters per second squared. G is 9.8 meters per second squared. And when you plug that in your calculator, you're going to get the tension at the top, which is 2.84 newtons. And that is correct to the right number of sig figs, as 3 is the minimum number of sig figs we see in our question. So there is the answer to part A. Okay, so that's that. Now, simply looking at the next part, okay, we have to find the tension at the bottom. Start thinking about this already. Okay, so if the tension at the top is 2.84, okay, so that's made up for by gravity. These two added together contribute to the force going in the middle. But in the second case, we only have Ft2. We only have the force of tension. Usually when your ball gets to the top of vertical motion, it tends to become a little bit slack. Okay, there's less tension in it. So we already should be expecting that this value is going to increase. Okay, now moving on. Part B. What is the tension at the bottom? We're going to do the same thing. We're going to start with F net equals ma. And then we're going to personalize it for this problem. Okay, it's a circular motion problem, so net force is centripetal force, acceleration is centripetal acceleration. Okay, in this case, you know what? I'm going to let up be positive instead of down. Okay, so I'm going to let up be positive, which means my net force centripetal is Ft2 minus mg. And that's equal to ma centripetal. Now I'm trying to isolate for Ft2, so I'm going to bring the mg to the right. Ft2 equals mac plus mg. Factor out the m, ac plus g. Okay, I hope you guys see a similarity here. Notice that for Ft1, we had m ac minus g. Here we have ac plus g. Again, because the force of tension has to be bigger here. It's the only force pointing towards the center of the circle. So it's got to be balanced. So plug in your values. Mass is 0.301 kilograms. Your acceleration, 19.25 meters per second squared. Whoops, not closing the bracket just yet. Okay, so plus 9.8 meters per second squared. Okay, when you find all that out, you end up with 8.74 newtons, which is a great deal higher than 2.84, right? It's about 3 times bigger. So there is your force of tension at the bottom. You had your force of tension at the top up here, clearly smaller, so your answer makes sense. So that's it for this video, guys. Be sure to subscribe to Physics in the Flesh if you enjoy these videos and find them useful, and click that like button, okay? Just to show me that you learned something from this. Okay, guys, enjoy the rest of your day, and I will catch you in the next video.